Once you've created a simulation, it's important to know how to validate it. And there are a lot of different ways to accomplish this. That is, you want to know, is the simulation doing what we wanted to do? There are a lot of different ways to consider this. Perhaps the most obvious, and the one that people often jump to first, is the Turing test. The Turing test has a definition in computer science. It's the test of a machine's ability to exhibit intelligent behavior equivalent to that of a human. And the classic Turing test is an example of a computer. You might be talking to it, and it's responding to you in ways that try to make you think that it's a real person rather than a computer providing those responses. We can change that definition around a little bit and think about a haptic Turing test. And the question would then be, can the user distinguish between the virtual environment and a real environment? That is, if I interacted with a virtual environment through a haptic device blindfolded, and then I interacted with a real environment, would I be able to tell a difference between the two? The answer for almost everything in haptics is almost always the user can distinguish between these two. There are all sorts of cues that a virtual environment can provide, whether it's a little bit of unusual activeness or some vibrations or even other sensory feedback like sound that will let the user know that they're not touching a real environment. But for some very simple environments, it can be possible, especially if the tactile interface, say, of the stylus is the same in both cases. But this is a very strict test and a very difficult one to pass. Here's an interesting example of not just a yes or no pass on the Turing test, but something that considers realism ratings. This is from a paper by Catherine Kuchenbecker and colleagues, and I like it because it shows the example of a very simple task where users tapped on some different surfaces. And the goal of some haptic rendering that she was also trying to do was to create virtual environments that felt like tapping on wood. So what she did was compare taps that were performed in both real and virtual environments. This is a modified phantom premium haptic device, where in this case she has a wood surface which has some foam underneath it, and it's mounted on top of a force sensor. And a user can hold onto the stylus and directly tap on it. In addition, she can replace this wood on foam with just regular wood or just foam, and she can also remove all of these physical samples and instead have the haptic device generate a virtual environment. And there are different algorithms. These are all different algorithms for generating haptic virtual environments that feel like tapping on wood, or that are intended to feel like tapping on wood. So what she had her users do was give a realism rating on a scale of 1 to 7, where 1 was totally not realistic and 7 was very realistic. And her users had to say how much this felt like wood. How much did it feel like tapping on wood? And they were blindfolded. So when they were tapping on actual wood, they had to give a scale of how much did it feel like they were tapping on actual wood. So interestingly, and you can see some error bars here, not everybody for every trial thought that wood felt like wood. But as you would expect, wood felt more like wood than anything else on this chart. Wood sitting on top of foam, which is supposed to represent what it's like when you have the sort of impact vibrations we talked about during haptic rendering, but with a sort of soft wall underneath, that also felt like wood, but not as much as regular wood. And then all of these purple lines are different levels of softness or firmness of some different algorithms for creating compelling sensation in a virtual environment. The decaying sinusoid is one that we covered earlier when we talked about haptic rendering. So all of these are not as good as real wood or wood on foam, but you can see that there are some differences between the algorithm. So by having users rate their realism, she could come up with a measure of which one would be best. She also tested the foam by itself, which of course was pretty bad. It's down here as well. So all of these purple ones in the middle are virtual environments. Another way to look at whether a simulation is good is whether it's good for task training. And this is a particular interest to the medical community. We would really like to have medical simulations that could be used for people to practice and learn on, of course, rather than real patients. And we would like those to be as realistic as possible so that what a user learns by interacting with a mannequin or a virtual environment will transfer to operating or working with real patients. There are a lot of ways that people have used to validate simulators. The one that's most commonly used is known as face validity. It asks the question of whether the system presents an environment that resembles that which is encountered during a real-world task. And so that's kind of a data-driven method. You could do it by actually looking at the raw data from what real interactions are like and what happens when a person interacts with the virtual world. Or you can do realism ratings, which are similar to what was shown on the last slide. But there are a whole bunch of other types of validities, which I'll quickly review. Content validity actually looks specifically at the skill, not just at the simulator, but whether the system measures a skill, which is the one that you desire to teach. Construct validity asks whether the system can capture differences between experts and novices. So if you get an expert surgeon and a novice surgeon both interacting with a virtual environment to practice surgery, can it show that yes, indeed, an expert surgeon is better? And this is important if you actually want to use the simulator as a way of evaluating surgical performance or deciding if someone is ready to do surgery of a certain type. Concurrent validity is a little bit different. It asks the extent to which testing performance with the simulator yields the same results as other measures. So in the medical community, there are already lots of ways in which medical clinical personnel are evaluated. And it would be useful if the virtual environment could be a more efficient way of recording that same kind of data. So you want to make sure that the data is consistent with standard measures. And finally, there's predictive validity. And this is really the number one thing that you would like to get at, but it's a really hard test to do in practice. What it asks is whether the performance or training in the simulator transfers to improvements in practice. And let's say again in a surgical environment, if you wanted to do this kind of test, you would have to have a group of surgeons trained with a simulator and then look at how they perform with real patients, and then a group of surgeons not trained with the simulator and look at how they perform with patients. For all sorts of logistical and ethical reasons, these are really difficult tests to do, and yet this is essentially what we're aiming for. So in many ways, this slide is meant to show that really understanding how simulators affect being able to do a task, especially one as high risk and complex and important as clinical or surgical tasks, that it's difficult to do these kinds of evaluations. Let's skip back and actually go to a very simple example one that is very data-driven and is sort of on the face validity side of things. And this is back to the example of rendering a spring. So let's say that you've decided that you want to create a virtual spring. You've decided this is your model. It's going to be this line, which has a constant slope of k, so that you can do your f equals kx spring rendering. But when the user is interacting with a haptic device, you could record force displacement data to understand what did the device actually display to the user. And then you might actually get these blue dots here, which are the actual rendered information. And they're only at some discrete points because we didn't take data at every instant in time. We only get so much resolution, say, out of our serial monitor that comes off the HapKit board. So while in the previous lecture segment, these blue dots indicated data that were being used to define the rendering. In this case, these blue dots are data which are showing us how well we did the rendering after it has been done. And you can see that because there's some noise, whether it's because of the position sensor on the haptic device or our limited ability to output the torques that we want on the motor, that it's not perfect. And you can come up with some measures of error, for example. The sum of squared errors, actually, where you look at the distance between all of these points and the line, would be one way of measuring the accuracy of that rendering. We can also look at things from the perspective of how they compare or modify human sensory thresholds. So if you create a virtual environment, let's say that has one particular haptic algorithm, and you want to get people to distinguish or to feel a virtual spring, we want to know with what accuracy can the person feel that virtual spring. And the way to look at this is through sensory thresholds. One type of threshold is an absolute threshold, which gets to this idea of sensitivity. So you could say, what is the smallest amount of stimulus that's required to produce a sensation? So can one haptic device compared to another haptic device, or one rendering algorithm compared to another one, produce a smaller absolute threshold or more sensitivity for a human operator? More commonly, we're actually interested in the difference threshold, or the resolving power of a simulation or a haptic device. And in that case, we measure the amount of change in the stimulus that's required to produce what's known as a just noticeable difference in the sensation. If you get into the haptics research literature, you're going to see this just noticeable difference, or JND, term a lot, because it's often used as a measure of a human's ability to discriminate between two different objects. And it's not just about measuring human ability, because you might test this person's ability with two different haptic devices or two different haptic rendering algorithms so that you could say which one is better than the other. So these are useful for comparing different haptic rendering techniques to see what would be more appropriate in a particular scenario to make the person as good of a sensor as possible. That is all about sensing. Fitts' law is interesting because it is actually not just about sensing, but also about movement. And so this is a very standard task that's used in human-computer interaction studies. What Fitts' law says is that the time to acquire a target is a function of the distance between targets and the size W of the target. So here's an example of two sets of targets. This example is a very difficult task. What the person has to do is start inside one target and then go to the other target and then go back to the first target and do this as quickly as possible. And you can see I'm doing it very fast and I'm making some errors. So I have some errors here and I'm not doing it super quickly. It's a difficult task because the targets are small and they're far apart. So D is large and W is small, and that means it's taking me longer to do the task, and I'm also making some errors. Here is a much easier scenario. We have huge targets. They're really big, and the distance between them is quite small. So now, if I want to successfully do this task, I can do it very quickly. I made no errors. I was going much faster than I was in the example above, and so this is an easier task to do. So Fitts' law, which is not like a fundamental law of nature, but it's something that seems to fit well to human performance, is that this time to acquire the target can be fit into a function of this form, where you take the distance D divided by W, and you can fit, after taking a bunch of data with users, these parameters A and B. But the point is that the index of difficulty is described by this term here. So people like to use Fitts' law, again, to compare different types of haptic devices or virtual environment rendering techniques to say which one is going to make this index, make the time lower given the same index of difficulty. So we often want to show that we can minimize time using useful haptic feedback. So if I had some kind of force field that sucked me into these targets here, I bet I could do this task a lot faster. So haptics can help people do these kinds of tasks. Granted, these are very abstract tasks, but you can imagine trying to click on cursors on a screen, move around quickly so that you can be more efficient when you use your computer. If you can show that haptic devices, and some people have, make people do those tasks more efficiently, then they might be able to enjoy using their computer and not be using it so long as they would without haptic feedback. So as a quick review, we've covered some different methods for validating or evaluating haptic simulations. There are realism or Turing tests that can be done. You can look at the impact on training to perform some specific tasks. You can do psychophysical or sensory motor experiments. So psychophysical being things like measuring absolute threshold, measuring just noticeable difference. Sensory motor experiments would be more like the Fitts' law task, where you actually have to do something, accomplish a physical task, and use that to demonstrate achievable performance. And then we also talked about just comparing the acquired data to the original data or model to see if it's accurate simply from a numerical point of view. Of course, our whole goal is that the person will understand what they're feeling in the virtual world.